break that apart, then you figured this out, right? And this is 5x from 0 to 2, which is 10 minus 0, which is 10. I think the whole thing came out 0, if I remember correctly. But it's memory, so I could be wrong. Okay? Because I think g of x was 5. G of x 5. Okay? Because you got that by doing the integral from 0 to 1, plus the integral from 1 to 2, plus the integral from 2 to 3. So, okay? Alright, so, that's how you found the integral from 0 to 2, okay? This one? Okay, so how do you do the derivative of an integral? Okay, first you'll plug the top function in, so you'll get tangent of the log of x to the 5th squared times 5x to the 4th. Don't forget that part. Minus tangent log 2x squared times 2. Okay? And you could have left it like that. You don't really have to simplify. But if you want to simplify, you can do that. Don't do more than that. Don't be a hero. Don't show off your algebra. Many of you, in the act of simplifying, take a right answer and turn it into a wrong answer, which makes it simpler for us to grade. Aha. In other words, don't simplify if you don't have to, okay? Professor Tanase and I have the same philosophy, which is, this is good enough. Okay? That means that you know what you're doing. How'd you like that second one, that trigonometry one? Did you guys figure that out? Yeah. Wasn't that kind of fun? Wasn't that hard? The answer to that was sine x, I believe. Plus c, of course. For those of you who love this in trigonometry, I wrote this question, so here you go. I said I'll give them one nasty one. Okay, 1 minus cosine squared is sine squared, right? So this is sine squared. So it's going to cancel the sine squared numerator and just leave you with dx over secant of x. But wait, secant in the denominator is cosine in the numerator. So this equals sine x plus c. There we go. Alright? I'm tempted to do this secret code word at some point if people don't show up. Let's see.
I remember saying,
you ready, Michelle? Okay. This is the good stuff. We're going to now learn how to integrate. So for a lot of the next handful of classes, we do what's called technique of integration. So this is when you become physicists, you'll be really happy that you learned this.
It's good after that.
Most people will not become physicists. Then you say, why am I learning techniques of integration? Well, what's going to happen is physics, computational biology, engineering, economics, statistics, finance, a couple other areas. You set up a problem, and often you have to solve an integral because you figured something out. Integrals are used to sum things, like we just did all these Riemann sums, right? So an integral, among other things, is just a way of adding up a lot of stuff. If you want to add up a lot of stuff, and you have the equation, and integrate it, that gives you these sums. Okay? The Riemann sums, in fact. So you will set it up, and then you'll look at the integral and you'll say, I have no idea what the solution is. If it was a derivative, you can take the derivative, but unfortunately, you can differentiate just about anything, but you cannot integrate just about anything. lots of things can't be integrated. Okay? It's kind of like you can smash things, but you can't always put them back together. That's our foreign policy of it. Okay? So, you'll be able to, but now we're going to teach you how to integrate a variety of things. So it's like the plus c. Just because you know, if you have x cubed, you can find a derivative as 3x squared, but if you know a derivative is 3x squared, you don't necessarily know that the original function is x cubed. There's lots of other functions it could be. Some things cannot be integrated. They are not integrable, or they're not very easily integrable, and you learn as you move up into higher math how to get really good approximations. Like when you plug your answers into Wolfram Alpha, as if we don't know about that, okay? Wolfram Alpha can give you an approximation as many digits long as you want. It'll spit out 200 digits if you ask it to, okay? And usually you don't need more than about 4. So, first major technique is something called integration by parts. If you remember the product rule, says that if you have two functions multiplied together, the u and the v, okay, the derivative of that is u times the derivative of v plus v times the derivative of u, to use a little shorthand. Okay? udv plus vdu. So if you were sort of to integrate that, you would get u times v is the integral of u dv plus the integral of v du. So you do a little algebra, and you can rewrite this as the integral of u dv is u times v minus the integral of v du. You all tell my u's from my v's? The u's have the little tail on them. Okay? So that is your integration by parts formula. So what will happen is, like we've seen integrals now where you have a function and then you have a derivative inside the function, and you say, aha, chain rule. Well, sometimes you'll have an integral where you have a function and you'll have another function multiplied together, but you can't use the chain rule. You can't use u substitution, in other words. So these will often have been the product rule. So integration by parts works the product rule backwards. Okay? This is a very powerful technique, and you can often use this to solve lots of integrals. One of the problems I tend to run into is, once we teach you this, you tend to try to use this on everything. Okay? And you go into the exam and you say, let's do this one integration by parts. Doesn't work. Well, let's do this one integration by parts. And that one doesn't work. There are other techniques out there, okay? So don't just do integration by parts. So far, so good? All right, so how do we do one of these? Well, let's take a nice, simple example. Suppose I ask you to do the integral of x cosine x dx. So you look at that and you say, I'm going to do u substitution. The problem is, if I make this u, that's not sine x, so that's not the derivative. If I make this u, that's not 1, so that's not the derivative, so I need something else. What I do is I identify the u and the dv, okay? This part. And then I'm going to play with it a bit and then use this formula. So I look at this and I say, let's let u equal x, dv equal cosine x dx. In other words, inside the function I have something I'm going to differentiate and something I'm going to integrate. Now I take the derivative of u, I get just dx, 1 dx. And I take the antiderivative of dv, remember that's really 1 dv, okay? And I get sine x dx. So now my formula says the integral of x cosine x dx is u times v, which is x times sine x, minus the integral of v times du, which is sine x dx. That's the x derivative. Okay? And now, integral of sine x is easy. That's just minus cosine x. So this is x sine x plus cosine x. Don't forget the plus c. Okay? Never forget that. That's it. That's the solution. Yes? Of course. So, I look at this integral, and I say, one part of this I'm going to take the derivative of, and one part I'm going to take the antiderivative of. So I say, well, let's let u equal x. I'll tell you in a little while why I chose that one. dv equals cosine x. So I'm going to differentiate u, and I'm going to get 1 dx. I'm going to integrate cosine x, and I get sine x. And now I go to my formula, and it says that the integral of u dv, so this is u and this is dv, will equal u times v times the integral of v du. I go through lots of stuff. Okay? So then I plug in. I say, well, u times v is x times sine x. And v du is sine x dx. So I integrate that, and I get cosine x. Okay? Now, how do I know this works? Well, let's take the derivative of this, just to prove it. Let's do the check. Check. I have x sine x plus cosine x plus c, and I'm going to take the derivative of that. So let's do the product rule, because remember, I want to end up with x cosine x. So if you say, well, what if it's just x sine x? That's kind of what you're doing. You say, well, the problem is if I take the derivative here, I get x times cosine x, that's what I wanted, plus 1 times sine x. This is that annoying product rule. But now I take the derivative of cosine x minus sine x, and I get what I wanted, because that's inside the integral. So that's how I know I got the right answer. Okay, I got this, and I checked it by taking the derivative, and I said, aha, I got x cosine x. Okay? We'll do a bunch of these, don't worry. It's only a first one. So what the integration by parts does is it figures out the extra piece from the product rule and helps you subtract it off. Okay? Because like I said, I looked at x cosine x, and I said, what if the antiderivative is just x sine x? You say, well, that would be okay, except when I take the derivative of x sine x, I get this extra sine x piece. So by having cosine x here, the derivative of x minus sine x, then they subtract, and I get what I want. Okay? Let's do another one. So far, so good? Yep. I'm going to erase in a minute, so write it down, take a picture, keep texting, it's all the same to me. You can have a text-proof room. You actually can. You guys will all freak out. So far, so good? Alright. Let's do another one very similar. Suppose I was going to do x e to the x. Again, I look at u substitution and I say that's not going to work. Because I don't have a function and its derivative inside. I just have two different functions in there. So if I let u equal x, du is just dx. Because that's the derivative of u. Right? Derivative of u is x, derivative of u is dx. dv would be e to the x dx. And what's the integral of e to the x? E to the x, our favorite one. Okay, so use the formula. The formula says that the integral of u dv is u times v minus the integral of v du. Professor Bernhardt calls this the voodoo formula. Which the first time somebody said that to me, I sort of said, huh? He said, we just do voodoo, right? I said, I'm not quite sure what that is. But then I figured it out, and I said, yeah, sure. Yes, OD. This says u equals x, du equals dx. This says dv equals e to the x dx. So v is e to the x. I think my handwriting is going to insult again. Very sad. We all love my handwriting. It's not that bad for a math geek, right? Gets the job done. Alright. So, I'm plugging in parts. U is x. dv is e to the x, right? So, integral of x e to the x dx equals u times v. So that would be x e to the x minus the integral of v du, which is e to the x dx. Right. Alright, now, what's the integral of e to the x? E to the x. So this is x e to the x minus e to the x plus c. I'm the one allergic to chalk dust. I should be coughing and sneezing like crazy. Got the idea? Let's have you guys do another one. But before we do that, I just want to show you a very simple rule that will be very useful for everything we do going forward. Okay, if you have integral of cosine of x, right? We know that's just sine x. If you have a constant, that's going to equal sine of kx divided by k. You get that if you did u substitution, but you know when you do u substitution on simple ones like this. It'll drive you nuts. So when you take the derivative of this, right, you would multiply by k. So when you do the antiderivative, you divide by k. So for example, if I had integral of sine of 3x, it would be minus cosine of 3x divided by 3. Okay? So that's true for cosine. It's true for sine. It's, I'm going to erase this. It's useful for E. By the way, secant squared, secant squared, those ones which we don't really like. If you have e to the kx dx, that becomes e to the kx over k plus a constant. And one more that's very handy. If you have the integral of dx over ax plus b, that's going to be natural log of ax plus b divided by a. Okay, so it's all sort of the opposite of derivatives, which makes sense because these are antiderivatives. Sure, plus c. Correct. So when I was done with my exams, I just put plus c next to everything. Just go back and check. You can do that. Okay? So you should memorize those because they're very handy so that we can give you something slightly harder and you'll be able to do it. Alright, let's have you practice an integration by parts problem. And the hardest part that people have with integration by parts, other than just executing it directly, is the minus signs and the fractions. They tend to mess that up. So you know what you're doing, but you have a little trouble with the minuses in the fractions, because you'll see sometimes you need to do integration by parts more than once. For now, I'll take one very similar to the one we just did. Let's do the integral of x sine 3x dx. Otherwise, I'm going to take 2 minutes and see if we can solve it. We need a function as a derivative. As a general rule, if you have x to a power, you're going to let that be the function. Okay? And the other thing will be the derivative. So, in other words, you let u equals x to the something, and dv will be the other piece. So if you let u equal the x term, dv is sine 3x dx. And then you're going to differentiate this one, integrate that one. Okay? So derivative of x is 1 dx. Antiderivative of sine of 3x is minus cosine of 3x over 3. I just taught you guys that. Okay? Because you're anti-differentiating, you're integrating. Okay? So now we plug this into the formula. The formula is u dv, integral of u dv, equals u times v minus u equals du. So the integral of x sine 3x dx is u times v, so this times this, which would be minus x cosine 3x over 3, minus the integral of v du, but we have a minus, so it becomes plus integral of cosine 3x over 3 dx. Remember I said, watch your minus signs and watch your fractions. So far, so good? Some of you got to this step. Okay, now we just have to integrate this. Well, this is just the integral of cosine 3x over 3 is just 1/3 the integral of cosine 3x. So that's 1/3 times sine 3x over 3, also known as sine of 3x over 9. So this becomes, I know, fussy, becomes minus x cosine 3x over 3 plus sine of 3x over 9 plus 6. Okay, so again, you do u dv. So u is x, dv is sine of 3x. Derivative of x is 1. The antiderivative of sine is minus cosine 3x divided by 3. So now you go to your formula. You have minus x cosine 3x over 3, that's the first part. Minus minus becomes plus integral of cosine 3x over 3. This integral, well, it's 1/3 cosine 3x, so that's going to be 1/3 sine 3x over 3, which is 1/9 sine 3x. Okay, and you just put the whole thing together. So what will happen with integration by parts is you get these chains of functions, because as I said, you need the other terms to get rid of the problem terms from the product rule. Because you look at this and you say, I want this to just be minus x cosine 3x, but it's not that simple. So if you differentiated this, you have a leftover term, and this helps you get rid of the leftover term. Okay? Anybody get this one right? Some of you? Yay! Alright, let's do another one. You guys gotta get good at this. How about integral of x squared e to the 2x dx? Now I'll tell you, with x squared, you're going to have to do integration by parts twice. Okay? So let u equal x squared, do integration by parts, and when you're done, you have to do it a second time. So, let's let u equal x squared, and dv equals e to the 2x dx. Okay? Then du will equal 2x dx. V will equal e to the 2x over 2. In general, when you have x to a power, you'll usually either have e sine or cosine as the other term, usually. Then x to the power will be your u term. Okay? The main exception will be when you have natural log. If you have natural log of x, that's always going to be your u term. These are the types that you encounter. Okay, so now we have integral of x squared equal to 2x is u times v. So x squared e to the 2x over 2 minus the integral of v du, which is the integral of e to the 2x over 2 times 2x dx, and those 2's cancel. So you have x squared e to 2x over 2 minus the integral of x e to 2x dx. Now we just did the integral of x e to the x, right? Like I said, to do that one, you just do integration by parts. Now, let u equal x, v will be dx, dv is e to the 2x dx, and v is e to the 2x 2. Less, a lot of sneezes. So this now becomes x squared e to the 2x over 2 minus, be very careful about minus signs. Very easy to mess them up. U times v, which is x e to the 2x over 2 minus integral of e to the 2x over 2 dx. And you distribute the minus sign, and you get x squared e to the 2x over 2 minus x e to the 2x over 2 plus 1/2 integral of e to the 2x dx. One more round. Now you need integration by parts. That's just a basic integral. So this becomes x squared e to the 2x over 2 minus x e to the 2x over 2 plus e to the 2x. So let's see. This is over 2, and that's a half, so over 4. Plus constant. And if you differentiate that, you'll see how the product rule works. Okay? So, when you take the derivative of this, you have a leftover term from the product rule. This gets rid of it, but wait, when you take the derivative of this, you have a leftover term from the product rule. So this gets rid of it. Gotta do some more. But you guys good at these? How much fun is this? No? You'll get good at these, you'll see. Even if you have to stay here all night. What? Where'd you get lost? Here? Minus x equals 2x. Minus minus becomes plus. I just took the 2 out. That's why that's a half. This 2 comes out. And this is a minus. This is a minus. That's why this is a plus. And this 2 becomes a half. You don't believe me. You think I'm making it up. Okay? You have x squared e to the 2x over 2 minus this one. Minus minus becomes plus the last one. Okay? E to the 2x over 2 is the same as a half e to the 2x. So it means divided by 2, right? Okay, you're not happy. Let's do another one. By the way, you could have like x cubed, x to the 4th, x to the 5th, but we wouldn't do that. There's a trick if you have high powers of x. Or a technique, it's not really a trick. Shortcut. Okay? Gotta do that one by parts. So it's a bit of a pain, but we'll get there. We have 2 other types to learn today. Remember, this isn't U substitution. Don't confuse the U with from the one with the U from the other. You just tend to use the same letter. Okay, let's let u equal x squared. dv, the cosine of 4x, dx. I pick the u equal x squared, because when I differentiate x squared, I get 2x. When I differentiate it again, I get 2. So my problem gets better each time. If I differentiate cosine, I just get sine. If I differentiate sine, I just get back to cosine. So I'm not really getting anywhere. Okay? So that's why we let u be the x squared term. If you do it the other way, you'll watch. You'll just get a mess. All right, now I let du equal 2x dx. And d will be sine of 4x over 4. Because it's always divided by this number. So now this integral, x squared cosine of 4x dx, becomes the integral of u times v, which is x squared sine of 4x over 4, minus the integral of v to u, minus the integral of 2x sine 4x over 4 dx. And the 2 and the 4 cancel. So I get this is x squared sine of 4x over 4 minus x, oops, 2 over 4 is a half, so I'll take that out, minus a half, integral of x sine 4x dx. So I've improved my integration by parts by going from x squared to x. So now I just do it again. So I let u equal x and dv sine of 4x dx. Then du is dx. And d is minus cosine of 4x dx. No dx. Sorry. Minus cosine of 4x. So this integral, remember our original integral was x squared cosine 4x dx. Now equals x squared sine 4x over 4 minus a half of, now this integral becomes negative x cosine 4x minus integral of cosine 4x dx. Yes? Oh, I thought on the floor. All right. Thank you. Just be careful with the minus signs, okay? You have minus a half times this integral, which is minus x cosine 4x over 4, minus, that becomes plus, integral of cosine 4x over 4 dx. So distribute. Watch your halves, watch your minus signs. You get x squared sine 4x over 4 plus an eighth of x cosine 4x minus an eighth integral of cosine of 4x dx. And that is sine of 4x over 4. So we get x squared sine 4x over 4 plus 1/8 x cosine 4x minus 1/8 sine 4x over 4, which becomes sine 4x over 32. Plus these. See how it goes 4, 8, 32, right? So you'll see a lot of that kind of stuff, okay? And that comes from all of the differentiating in product rule. That was messy. That's all one problem. Grading these is really fun. Sarcasm. Yes. I hope you get partial credit. Not up to me. That's how Professor chooses. Now say, yes, of course you'll get some partial credit. Right. I don't tend to assign anything harder than this because, as I said, it's not going to grade. And also, you're really just testing people's algebra skills at some point. You're not testing their calculus skills. All right, let's do an easier type, but another one. When I say easier, I mean less outbreak. You guys wanted to take integral calculus? No want here. Have to. Must. Right? You're here because you must be here, not because you wish to be here. With a few exceptions. We know that the derivative of natural log is 1 over x, and the integral of 1 over x is natural log, but what do you think the integral of natural log is? You kind of want that to be 1 over x, but it's not. It's the other way around. Okay? We do that with integration by parts. Let u equal natural log of x. dv, well, what's dv equal to? dv is just going to be dx. It's going to be 1. Remember, this is a 1 in here. So dv is dx. So when you differentiate this, you get 1 over x dx. And when you integrate this, you get x. So now I go to the formula. And this is u times v, which is x ln of x, minus the integral of v times du. What's v times du? X times 1 over x. And x and 1 over x cancel. So this equals x times natural log of x minus the integral of dx. The integral of dx is just x. The root of x is 1. Remember, this is, I keep saying this is 1 dx. So this is x ln of x minus x. You may want to memorize that. I memorized it. I recommend you do. I use the eraser part of the eraser. So the integral of the log of x dx equals x ln of x minus x. Very handy one to just put in your memory bank. So far, so good? So far, so good. All right. One last one for today, because I know how much you love this. This is one of the more interesting types. So we did the x times e to the x, and the x times sine x, and the x squared times e to the x, and all that stuff, right? Now, do a slightly different one. What if I want to do the integral of e to the x cosine x dx? These things show up a lot in electrical engineering, among other places. If any of you can be double E's, you should pay careful attention. Okay? Show up in physics. Lots of things that go like this. You get the sines, the cosines. And if they dampen, so if they go, then you get the E term. And so on. So there's lots of phenomena that behave like these. So you have to learn how to integrate them. You're not the only ones. There's some of them. Alright. Let's do this one. Well, it doesn't really matter which one I pick. See, the problem is, the derivative of e to the x is e to the x, the integral of e to the x is e to the x, so I don't seem to be getting anywhere. But when I do sine and cosine, it just kind of flips back and forth. So how the heck am I going to do this one? Well, let's see. Let's let u equal e to the x v sine x. So now, integral of e to the x cosine x dx equals u times v, which is e to the x sine x, minus integral of v to u, which is e to the x sine x dx. I haven't really made my life easier, have I? I just turned e to the x cosine x into e to the x sine x. Doesn't seem to have done much. Nope. But hang in there. Alright? So I have to do this integral now. So let's let u equal e to the x. Now put it over the side. U equal e to the x. dv equals sine x dx. du will equal e to the x dx. And v will equal minus cosine x. So I have to be careful. Watch your minus signs. So I'm going to take this integral. My original integral was e to the x cosine x dx. And that equals e to the x sine x minus, now use the formula, minus e to the x cosine x, minus minus is plus, integral of e to the x cosine x dx, which is this equals e to the x sine x plus e to the x cosine x minus integral of e to the x cosine x dx. So now you say to me, but wait a second, I'm back where I started. Right? I had an e to the x cosine x, I turned it into e to the x sine x, and now I'm back to e to the x cosine x. This is wasting time. I'm just going around in circles. I don't understand. Hell. Right? So then you go, but wait, this is minus the integral of e to the x cosine x. So why don't I just add that integral back to the other side? Yes, you can do that. What do you mean you can do that? I'm going to do it. So watch. So now you get 2 integral e to the x cosine x dx equals e to the x sine x plus e to the x cosine x. You're done. Wait, what do you mean I'm done? Once you're done, you divide by 2. You get e to the x cosine x dx is e to the x sine x plus e to the x cosine x over 2 plus c. Kind of seems like a cheat, doesn't it? You say, wait, so you just put it back where you started and you ended up with the final answer. But hey, I got an integral on the left and I have no integral on the right, so let's do something correct. Okay, so let's go through it again. So you let u equal e to the x, du is e to the x dx, dv is cosine x, and v is sine x, so you get this integral. Then you repeat, you get back here, except now you have minus the integral of e to the x cosine x. So if I added that to the other side, I have an integral e to the x cosine x plus another integral of e to the x cosine x, which gives me 2 integrals of e to the x cosine x. Then I just divide by 2. I took this integral right here, took this integral right here, added it to the other side. And yes, you're allowed to do that. Okay? All right, I'll see everybody on Monday.